Cool. Okay, so who has questions?
I had two questions. Do I just tell you like which number they are? Like, are they, or do I have to share my screen or something? Or
Yeah, I actually don't know if the enumeration is the same. But just tell me which ones you want to ask about, and then I'll let you know. We'll figure it
okay.
out. Yeah.
So the first one for me is question 3, but it says like vector C has a magnitude of 23.4 meters and points in the negative y direction. Vectors A and B both have positive y components and make angles of alpha 42.9 degrees and beta 27.7 degrees with the positive and negative x-axis respectively. If the vector sum of A plus B plus C is equal to 0, what are the magnitudes of A and B?
Yeah, cool. So we have the same enumeration then, it seems like. So
Okay, so then it'll be number 3 and number 5.
okay, number 3, number 5, cool. I'll probably, let me see here, just because I want to get to like everybody, I'll probably, okay, somebody else has the same question.
That's my question too for number 3. I have the same type of problem, but it's slightly different numbers, it looks like.
Okay, cool. Yeah, okay, so then I guess we can do 3 and 5 then. I just want to make sure everybody has a chance to get questions in, but it seems like lots of people have the same questions, so it'll probably be okay. Okay, so nice. All right, let me share my screen here, and I will show you what to do. Okay, so this is number 3. Can everybody see this okay? Do I need to make it bigger?
A little bigger would be nice.
Oh, okay, no problem. How about that? Is that good?
Yeah.
That's good. Why not? Why not just a little bit bigger, I guess. Okay, so the first thing to do here is to break these vectors into their components, right? So does everybody feel okay with the unit vector notation? Is it strange to anybody, or weird or uncomfortable? It's okay if it is, because
Is that the splitting it into like I and J components, that format?
Yeah, so yeah, you would put it in the you would use like the unit vectors like I hat, J hat, K hat. Because that's not what I would do, honestly. I would tend to write my vectors as an ordered pair. I'll show you what I mean by that, right? So like, let's start with A, and I'm not gonna do arrows because I don't think there's any reason when you're typing stuff to ever do that. Can you all see my screen, by the way? You can, right?
Yeah, we can see it.
Okay, because it doesn't show the green outline. That's weird, but I guess it's fine. All right, so anyway, what I mean by that is like I would write in general, I would write a 2-dimensional vector like this, right? So I would say that the X component is in the first position, the Y component's in the second position. I think that this is easier. It's just like less to write, if nothing else. So this is going to be my convention pretty much for the whole class, for the whole semester, I should say. So hopefully that's cool with everybody. So what we want to do though is just use like sine and cosine essentially to break all 3 of these into their X and Y components. So like, what do we think we want to put here for the X component of A?
Would that be A cosine alpha? Or?
Yeah, exactly. And I'll just jump straight to this because like if you use cosine for one of the components, it's like a very good bet. It's almost a guarantee that you'll use sine for the other one, right? So I'll write A sine alpha here. This is my first vector, and what we would say is that we've resolved it right into its components. So I think that the first vector isn't so tricky because it's in the first quadrant, which means that both of its components are positive. But you have to be a little bit careful with the second vector. So let's do this. Write out the general form here. This should be vector. Okay, so then how about for this one though? Anybody have it? So I should say, I guess, that for me, I'm taking this number, big A, right? And this number, big A, and then the number, big B, to be positive numbers. So like, what should I write here then for the X component of the B vector?
Wouldn't it be negative B cosine?
Yeah, right. So we would just put negative B cosine theta. And that is because it's in the second quadrant, right? So it should have a negative X component. And remember what I was saying is that this B, by my convention, is a positive number. So that ensures that this is a negative number, because cosine is, so cosine and sine actually are going to be positive for arguments that are between 0 and 90 degrees, right? So that's something to just maybe think about when you're doing this stuff. So then we'll have that the other one is B sine beta, right? Cool. So then we want to do the same thing for C. And I'm going to put something like this. I'm going to put 0 C sub y because we can see that C has no X component, right? And what I would write here is I would write 0 and then just minus C. So just to stress this again, by my convention, this big C is positive 25.8 meters, right? So then I've gotten the sign correct, the SIGN here, by putting the negative sign in front of this number. Okay, cool. So I really dislike what they did here because they didn't really indicate that this is a vector sum, because these are not in bold and they don't have arrows over them, right? So it, it might not be 100% clear. So let's just say what we demand is that A plus B plus C equals 0, and this is a vector. Well, everything here is a vector, right? Because actually the only way you could have all the magnitudes add up to 0 would be if all the magnitudes were 0, because the magnitudes by definition are positive, right? So I don't know if that tripped anyone up, but this is what I would write here. And so then what we can do is we can just look at the sums, or we can look at the sum of all the components separately. So what we could write is we could write something like that. Let me do this. Maybe a little fancy here. That this tells us, right, that A sub x plus B sub x plus C sub x equals 0, and A sub y plus B sub y plus C sub y equals 0, right? And so then we just write out these sums and enforce that the components work out to be 0. So like what I would do is then I would say, well, A cosine alpha plus negative B cosine beta plus 0 equals 0. So that takes care of the x. And then we do the same thing for y, right? We say A, why it like wants to put everything in bold. A sine alpha plus B sine beta plus negative C equals 0. So we wind up with a system of equations here, and we have 2 equations and 2 unknowns. And that is something we can solve, right? And so what we want to do is we want to be a little bit careful, though. I'm gonna just like clean this up a bit now that I've written it like very explicitly. Just want to get rid of like this 0. It doesn't really need to be there. And then I'm going to just change this to minus big C. So this is now what we have, right? Two equations, two unknowns. Do we all feel good about solving this? Is this like a position where I could just stop and move on to the next question, or does anybody want to see maybe?
Could you go over how to solve it?
Okay, yeah, that's cool. I again, like, I don't want to be doing your homework for you, even though that's kind of like almost been my MO in the past. I'm trying to be better about that, but I'll do one more step here. I'll show you the simplest way to go about this. And the way that we would want to do this is we would solve so we would solve these two equations, right, for the terms involving A. So for the X one, I just get A cosine alpha equals B cosine beta, right? That's one step. We just add B cosine beta to both sides. The other one is going to give us A sine alpha equals C minus B sine beta, right? So then this is what probably wouldn't occur to a lot of people, because I know that the first time I saw somebody do this, it like really blew my mind. But what we want to do is we want to divide one of these equations by the other. We want to divide the second equation by the first. So what I could do is I could write A sine alpha over A cosine alpha equals what is it? It's gonna be C minus B sine beta over B cosine beta, right? So what does this do for me? And can anybody see that, like, or see what's happening here?
You get tangent of alpha and tangent of beta.
Well, you don't get tangent of beta, but that's okay because you could get tangent of beta if you expand that. That's good. But I wouldn't do that. I would just cancel the A's. The other thing that it does for me, right? And then rewrite this as tangent alpha. And there you go, right? So at this point, it should be something you can do the algebra for and solve. And notice that once you have, let me see here. Wait a minute though, we don't have, let's see, we don't have A, we have neither the magnitude of A nor B, right? So maybe we need to do something else here. No, we're good, my bad. So we just solved this for B is what it comes down to. I was thinking that we were fine solving it for alpha, but we know alpha, so we solved this for B. Then what we can do is we can like look at this equation, for instance, right? And then if we have B, we can get A. Does everybody see that? Cool. So that's what you want to do here. And I think like the theme is just to be careful with the signs of the components and make sure that you know how to do the algebra stuff, right? Algebra is going to be like super important for this class. It's going to be arguably more important than calculus, even though it's, physics with calculus, not physics with algebra, right? So just make sure that your algebra skills are where they need to be. Okay, so is everybody good with this? Cool. Let me see, there's some stuff in chat. Let me just make sure I didn't miss anything. So for Lauren, is this okay, or do you want me to keep going a little bit? Is that what you're saying?
Yeah, if you could just like keep going to like how you would, I get once you isolate B, but I'm a little unclear on how you would isolate it.
All right, why not? So just because we're getting started here, right? It's beginning of the semester. But moving forward, I reserve the right to not do the algebra for you, okay? So what I would do is I would multiply both sides by B cosine beta, right? So I would wind up with B tan alpha, B cosine beta on the left. And then I would have C minus B sine beta over here. Okay, then I would add B sine beta to both sides. So I would wind up with B tangent alpha cosine beta plus B sine beta equals C. The final step, well, the second to last step, I guess, is to factor out the B. And then you just divide both sides by this junk in the parentheses here, right? Because this is just some number. After you evaluate, you plug this stuff into your calculator, and then you divide both sides by this part of the expression that I've highlighted, and you get something for B, right? You can get what B is, you can get a number for its magnitude. Yeah, and so the numbers will be, yeah, so I'm using my numbers, right? But the numbers should in general be different for everybody, but that's okay, right? That's why we do this symbolic stuff. That's why we hate numbers. Because this makes no assumptions about really the numerical values of any of these things. And this is what, so brace yourselves, but this is what I want to see, right? When you're doing your work, as the person who's going to be grading most of your work, like I want to see this. I don't want to just see a page of numbers, because that's going to disorient me and trigger me. And that's not the state of mind you want me to be in when I'm grading your work, right? So I know that this looks weird, and it might be a little unnatural for you, but you will get much better at it with practice. So just make sure that you're practicing this. So, and then the question is, how do I get A? Well, then what you do is, like, you just look at this equation. Now that you've solved for B, you can use this equation to get A. Do you see that? Okay, but yeah, okay, cool. All right, so let's move on then. So that's that. The next one was number 5, right?
Yeah.
Okay. So let's see here. All right, I'm going to stick to their stupid notation. I really don't like this, but it's not the end of the world, I guess. So what I would do here is, let's see. Cool. I would say something like this, and I'm not going to write this all out, but I'll just do it. So E sub 1, they want the answer in centimeters, so we can keep everything in centimeters. There's no reason to convert here. Is going to be 83.0 centimeters. And then theta sub 1 would be 90 degrees. And then V sub 2 would be 55 centimeters. Etc. Right? Because like we know then that theta 2 is going to be 143 degrees, and then theta 3 would be 227 degrees. So that's going to be my choice of notation for this one. And so what we can do then is, maybe we want to make a sketch here though, because I think that in general it's a good idea to make sketches. And so I'm going to do my best, not having like a tablet or anything to write with, but I'm going to put think this should be good. I'm going to draw like my y and x axes here. Okay, so let's like make a sketch of what these vectors look like. So let's start with the first vector, and I'll put that in red. So that is at 90 degrees with respect to the x-axis, right? So that's going to look pretty much like this. Just going to point straight up. I want to make it thicker though. Let me see if I can do this. Okay, much better. So that's what this first vector is going to look like. Cool. The second vector, so this is at 143 degrees. So this is going to be in the second quadrant, right? Let's put this in blue. Are the colors okay for everybody? Like nobody's like colorblind or anything, right?
Those are good.
Oh, okay, cool. So then this might look like this, right? For the second vector. Then the third vector is going to be at 227 degrees. So that might look, I don't know, maybe like this, possibly. So then this is our sketch. I think this looks fine. If I wanted to be like really anal, like this would be a bit shorter because this vector is shorter than the red one, but it doesn't really make a difference. Since we're gonna just be doing the components here anyway, right? So this comes down to writing these out in terms of their components again, right? This is the drill. So I'll do V sub 1, and then maybe I'll get some of you to help me with wouldn't the third be in the third quadrant? It's possible. Let me see here. So 90, 180, 270. Yes, it would. Wow. Okay. So thank you for that. Let me fix that. Okay, so it's going to be more like this, right? I think this is a better. I don't like that it's not starting from the origin though. Like that. Does that look better, everybody? Because it should be like approximately 40 degrees past the negative x-axis, I guess. So cool. Okay, thank you. So then, yeah, so what we want to do here though is break these into their components. The first one is nice because it's already kind of, it's a one-dimensional vector, right? Yeah, this is being recorded and I will email everybody the link. I'm going to put it on my YouTube channel that I have from like the class I was teaching over the summer. So you'll be able to find it there, and I'll send that out to everybody. So what we have then is this, right? This is pretty simple. Let's then do the second one. So again, remember, we want to ask ourselves like, hey, which quadrant does this vector live in? And perhaps I'm not the person to ask that question because apparently I can't get it right. But if we trust the sketch that I've made, then I think that this vector v2, right, the one in blue, lives in the second quadrant. And so what that means is it's going to have a negative x component and a positive y component, right? But here's the thing. You're not going to want to write this. Because your reference angle is larger than 90 degrees, right? Remember we were just talking about earlier about how cosine and sine of theta are both positive between 0 and 90 degrees. Well, they're not necessarily positive when we're talking about angles larger than 90 degrees. And one of the advantages of using angles larger than 90 degrees is that the trig functions actually take care of the sines themselves, right? So what you would do here is you would just do this. You would just write v2 cosine theta. And I mean, I don't know off the top of my head that what the cosine of 143 degrees is, but I can easily check using my fancy calculator here, right? And I see that, well, okay, that's not helpful. For those of you keeping track at home, it might be entertaining to count how many times I put something into Mathematica and don't get a numerical value when I was expecting one, because it's going to happen a lot. But I see that now that I tell it to give me the decimal approximation, that it's approximately -0.8, right? And so this will work out to be a negative number, which is what we demand, because this component points to the left, right? The x component of the second vector. And then we just do the same thing for v2 y, right? We just do v2 sine of theta 2. This should be theta 2. As should this. Okay, so then who wants to tell me what I put for v3 here then?
It'd be v3 cosine of theta and v3 sine of theta.
Yeah, nice. And again, this is fine because we're using a reference angle larger than 90 degrees. So the sine, the SIGN is sort of automatically taken care of by cosine and sine, right? Now, my personal preference, and this is something that I'll usually try to stick to, is to not use angles larger than 90 degrees, because for me, it's nice knowing that when I do that, I wind up with sine and cosine always being positive. But it doesn't matter, right? I would say for all of you, just like figure out which convention you like and stick with it, and then it'll be fine. But we could check this too, just to be completely sure. And now we would expect like both of these components to evaluate to negative numbers. And so like if I do, let's say I do, okay, I'm not going to make that mistake I just made. I'm going to say, tell me what the numerical value of sine, for example, of 227 degrees is, right? Works out to be negative numbers. So it seems like we're good. Okay, cool. Is this all clear so far? Everybody okay with this? Okay. Good stuff. So then the next step is, well, can somebody tell me, like, what do we do? What do we do next? What do we think we want to do?
Don't we add up all the vectors to find the magnitude?
Yeah, that's exactly what we want to do. We just want to take the vector sum here. And so we could say something like, well, what is v1 plus v2 plus v3? And I should write this as a vector. So let me make these all into vectors. And then it would just be the same exercise, right? Like, because this, remember that this tells us, or what we can do here is we can add. Let me write this a different way for this one. So I'll say that these add to some resultant vector. We'll call it R, right? And so we have like the same kind of thing where we know that all the x components, and this is why I don't like writing my vectors with subscripts if I can avoid it, because it's going to get like a little obnoxious here. But we know that, like, for instance, v sub 1 x plus v sub 2 x plus v sub 3 x equals r sub x. And the same thing goes for y, right? So v sub 1 y. y plus v sub 2, y plus v sub 3, y equals big R sub y. And so it's just a matter of crunching the numbers at this point, right? And then what we want to do is remember the Pythagorean theorem, which tells us, because we're asked to do two things here. We're asked to solve for the magnitude of this resultant, and we're asked to solve for its direction. And we just want to remember that the magnitude is given by the square root, and this is just the Pythagorean theorem, of this sum, right, of the sum of the squares of the components. And then we can figure out what the angle is by using arctan. Right? Because once we've gotten this into its components, like we can maybe even try to make a sketch here. Let's do that because that might be useful. We can try to sketch the resultant. This is what we're going to do. I'm going to try to do it quickly. But remember that, like, if we want to add vectors together graphically, we can just do the tip to tail thing. And so if I start with the first vector, I draw the second vector so that its tail is at the tip of the first vector, right? And then I can do the same thing with the third and second vectors, like so. And so if my sketch is reasonably accurate, then our resultant, let me put that like in purple or something, is going to look like this, right? And we see that we could always just take this resultant and look at its components. So I don't want the drawing to get too busy here, but I'm going to try to put this in. So we could say, like, well, this obviously has some x component that looks like that, and a y component that looks maybe like this, right? And so when we like check our numbers here, like when we do the calculator stuff, which in general I'm going to try to avoid doing because I hate numbers. But when you do that, you should find, right, that this r sub x value, this works out to be a negative number, and this works out to be a positive number, right? And we're just going by the sketch. But this will tell you something about this angle, right? Because we want the angle that this vector, this resultant vector, the one in purple, makes with the positive x-axis. And so we can see, right, that if our sketch is even reasonably accurate, then we know that the angle it makes should be between 90 and 180 degrees, right? So like if you do this and you find that your theta is like 30 degrees or 45 degrees or like 220 degrees, you know that can't be correct and something's gone wrong, right? And I think that what you want to do in this class is you want to take every opportunity you have to catch yourself before you make a mistake, right? As a strategy, because I don't know, you'll have lots of opportunities and you don't want to make mistakes. Okay, that's why I say you want to do that. So does this all make sense? Is this I haven't stopped for questions in a little while, so everybody good?
I have a question.
Yeah, what's up?
So for the magnitude, like I did all of that and like rechecked all of my algebra and it's like not right. So I don't know if I don't know why.
Yeah, so like probably it's just something with a calculator that is not working for you.
I'm not sure. sorry, I'm not sure because I like did it a few times, like input it different ways, and I'm getting the same answer, but it's not saying it's correct.
Yeah, so what I'll say is that if you want to stick around
Okay.
after, like I can try to help you with the numbers.
Okay.
But yeah, I mean, and so the first question to ask yourself is your calculator in degrees?
Yeah.
Yeah, so and I think that that's something that is important, especially if you're taking a math class where I think like you always want to put your calculators in radians, right? But what we can take a look at this at the end.
Okay.
That's cool. Okay. All right, good stuff. Okay, so who else? Does anybody else have questions about this? Is this all good? Okay. Does anybody else want to ask about like another question from this assignment then? I'm gonna go ahead.
Could you move on to question 7?
Yeah, sure. I'm gonna clear my screen. So if you haven't gotten this, like take a screenshot or something, but I'm gonna get rid of all this now. As soon as I figure out. There we go. Cool. Okay, so you want to look at number 7. This one, the cross product. Why is this not loading? That is annoying. Oh. Let me just try like refreshing, see if it'll just give me this picture here. Okay, cool. That worked. Whoa, no, that didn't work. Okay, it did work. Okay, so cross product, right? It's a pain in the ass to calculate directly. But finding the magnitude of the cross product isn't so bad. And we can use our intuition for the cross product to determine the direction, right? So what I will say is that, well, actually, I'll pose this question to you. Let's say that I take the plane in which these vectors lie to be the XY plane. And we know that the cross product of two vectors gives us a vector that is perpendicular to both the original vectors, right? So what are the two choices? What are the two possibilities for the ways that the cross product of any of these two vectors could point? Like, which directions?
Z positive and Z negative.
Yeah, right. So, and then what that would mean for us more sort of informally is like into or out of the screen, right? And so the idea is just like that you can always take any two vectors and let them define a plane, right? And then just remember that their cross product has to be a vector that's perpendicular to that plane. Now, you might be like, well, okay, that's all well and good, but which is it, right? Is it into the screen or out of the screen? And that's where the right-hand rule comes in. And so what you do, let's focus on A cross B, is you take your right hand, you line your fingers up in the direction of A, you curl them towards B, and then your thumb points in the direction of the result of the cross product, right? So let's say for A cross B, which direction is that? Is that into the screen or out of the screen?
Out of the screen?
it's into the screen. So B cross A would be out of the screen. And that's one of the funny things about the cross product is that the order matters, right? It's not like usual multiplication. I can multiply 3 by 2 and get 6, or 2 by 3 and get 6, right? I don't get like -6 if I switch the order, but the cross product cares about the order, right? So you have to start with the first vector in this case. So you would take your right hand, you would point your fingers in the direction of A, curl them in the direction of B, and then your thumb points in the direction of the cross product, right? Now, if you'd use your left hand, you would get that it points out of the screen, right? So make sure you're using right hand. And that's the utility of the right hand rule. It's like we already know that there are two possible ways that any cross product can point, right? And it tells us which of those two is correct. So that handles the direction though, right? Because like this is going to give me like 6 choices probably. And we see that into and out of the screen are some possibilities. So for A cross B, it should be into the screen, right? So before we calculate this, let's just do as an exercise. Let's do C cross B. Which way do we think that's going to point? You kind of have to contort your hand for this one, right? Because it's what are we thinking? C cross B.
Out of the screen.
Yeah, good. Thank you. Cool. So the way that I would write the cross product, I don't know how it's given to you in terms of a formula, but I would write something like this. I would write for 2 vectors, let's call them like U and V. U cross V is UV sine theta. And then I would write n hat. This is like one of the instances in which I think the unit vector notation is useful, because n hat is just the vector that is perpendicular to both u and v. It's the unit vector that's perpendicular to both of these, right? So this could be one way you might write the formula for the cross product. Now there's like a way you can calculate it, right, with the components, and that's kind of gross. So I'm not going to talk about that unless somebody's interested in seeing it. But this should be fine for most of our purposes in this class. And you can always just make a computer do the cross product for you, right? Like maybe calculate it like once or twice by hand, and then once you feel good about that, don't waste your time, because it takes a long time and it's easy to make a mistake, and the computer will do it quickly and flawlessly, right? So you could literally find a widget like this, like the Wolfram Alpha widgets. This one will calculate cross products for you in like the blink of an eye. So this might be a useful thing to have. And I don't know if it like visualizes them for you too. That would be nice if it did. Oh, it does. Wow, that's awesome. So this actually even like, so it's not, I don't know, you can't like move this around. Like if I did this in Mathematica, I could like take this and rotate it and stuff. But if I double click, right click, nope. But this actually gives you like a sketch of the 2 vectors too, which is pretty cool. So this is, I don't know, this is useful. But all we need to do for this one, where did it go? is realize, right, that like, let's say the magnitude of A cross B is just A, B sine theta. Oops. Sorry about that. I didn't mean to be, yell at you. I'm still yelling at you. Why is it capitalizing? That's so weird. I don't know what's going on with that. Okay, like that, right? Where theta is the angle between A and B. So what would that be for this problem? I think we all have the same angles, right?
Would that be 50 degrees?
Yeah, cool. And then we could do C cross B, magnitude of C cross B. And this is just
90 degrees.
Yeah, B, C, and then we'll write sine of phi. Well, I really don't know why it's auto capitalizing sine. It's never done that before. It's bothering me a lot. Let me just do this. Okay, so BC sine phi, where phi is the angle between B and C, which we said was 90 degrees. And so that's it for this problem. There is this last part here. Let's see, at what angles above and below the horizontal line could vector A be so that A cross B equals 0? So for this, we want to just say, well, where is sine of theta 0? Right? And I don't remember, but I want to say that sine is 0 when theta equals (2n plus 1). Like this. Let's say when theta is n pi over 2. And n is odd, right? So that means like sine is 0 when well, 0 is not an odd integer, but so sine of 0, sorry, sine of theta is 0 when theta is 0. When it is, no, I'm tripping. Should just be n pi, right? You know what? This is embarrassing. Let me ask Mathematicus. So 2n pi. And n is just an integer. So n could be 0, 1, 2, 3, etc., right? So you could write this in terms of degrees, because 2 pi radians, wait, 2 pi radians is 360 degrees. This is okay. I don't. because it should work for. I think I was right. I think it is. All right, let me just do this. This is probably the simplest. So we know that sine is 0 when theta is 180 degrees, right? We know that it's 0 at 360 degrees. We know that it's 0 at 540 degrees, and so on. Okay, that's what I'm gonna say. And also at 0. So we don't have to worry about, I think, about anything beyond 180 degrees, right? Because the largest angle we're giving here is 180 degrees. And so what we want to do is actually, I'm gonna stop here. I'm gonna stop talking because I've probably just confused people more so than I've helped. And I'm gonna let you fight with this one. If you are unable to get it, just reach out. But this is, I'm going to leave it at this, right? Is we want to, because remember the cross product depends on the sign of the angle between the two vectors, we want to see when sign of that angle is 0. Because these two vectors obviously have non-zero magnitudes, right? So the only way their cross product could be 0 is if the sign of the angle between them is 0. Now, sine, right, is 0 at these values. And I think the only two that we really care about are like 0 and 180 degrees for this particular situation. Did that help at all? Are people just more confused now? All right, I got 1 thumbs up. That's something. Cool. I could probably take one more question if anybody has one.
I have a very kind of brief question about number 8. I think I have it figured out. I just want to make sure because I haven't gone through much of the math yet. I just want to make sure. It's asking for instant acceleration, and the formula for that is just finding the second derivative of the equation that's there.
Yeah.
Would I be correct in that? Or okay, and then I would have to plug in T as that equation, and that would give me the correct answer.
Yeah, that's exactly it. And so, you know, like this, I would probably also just make the computer take the derivative for me, because I don't know, you could just, it's easy to make a mistake as you're going through and like using a calculator. And I mean, the point of this problem as I see it is that the second derivative of position is acceleration, right? And so that's like the conceptual part that we want you to get here. As far as, you know, plugging into your calculator or whatever, like that's not the point, in my opinion. So I would just, you know, just probably have like Wolfram Alpha do it for you, or Mathematica or whatever.
Okay, thank you, I appreciate it.
Yeah, no problem. Okay, that was an easy one. So I'll take one more if anybody has one.
I was gonna head over to 10 real quick, please.
10, yeah, cool.
I understand what it's asking for average speed and velocity, but I'm just not sure if I'm supposed to be taking like points or if I'm supposed to be taking the slope and then adding them all together and then dividing by how much there is between these periods or not.
So I would say that like here, velocity is easier to do because, like, let's say for one dimension, velocity can be defined to be simply delta x over delta t, right? So here, for the average velocity from 1 to 4, we could write something like this. We could write x sub 4 minus x sub 1. That's our delta x. And it actually is going to work out to be negative, right? Because 35 is smaller than 40 for my numbers, right? And then delta t would just be 3 hours. So this is the this is the average velocity, and so that's, I think, not too tricky, right? But the speed is a little bit, I think, is a little bit trickier. Let's see, how would you do this? You could write it like, you could write the speed like this, I guess. Symbolically, right, where the delta is like what I just wrote here, right? It's just, so this would be like the, I'll fill this in actually so you can see what I mean. Well, I'll start to. I'm not going to go all the way unless you want me to. Let me just copy and paste this in. So what I'm saying is that this would be here for the first one, x2 minus x1, the absolute value. And then this would be x3 minus x2 plus dot dot dot, right? But you probably see at this point what is going to go here. It's just one more thing. And so you just have to evaluate this, because this gives the distance. The numerator here is the distance, not the displacement. And so I don't know that there's like a neat and tidy formula that I can write for the average velocity, or sorry, that I can write for the average speed, like what I wrote for the average velocity here, right? These usually end up working out to be more obnoxious. But this is what you want to do, I think, something like this. And then you just change the points that you're looking at for the second part, right? Now, an important thing to remember about speed, right? Like a big conceptual thing is that speed is always going to be a positive number. And so make sure that you are, reading the problems carefully, like especially on a quiz or an exam, to ensure that when you're asked for a speed, you write down a positive value, because if it's negative like that, that's like a pretty big, that would be considered a pretty big conceptual mistake, right? Even though it is perhaps easy to do, it's easy to just, not maybe think too hard and just be like, oh yeah, speed, velocity, well, they mean the same thing sort of in everyday language, so whatever. But making sure that you keep them separate in your mind is going to be very important for this class. Does this help?
It does, yeah.
Okay, cool.
Thank you.
Yeah, no problem. All right, then I think I'll probably just end here. If you want more help, remember that recitation this week will primarily be dedicated to homework help. And then there are also office hours and resource room hours. So you have, lots of chances to get help. All right, I'm gonna stop recording and then I can help with the one question there.